Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we'll continue to subtopic 5.2, the central limit theorem. So in previous video, you have 6 previous video, which is from chapter 5, which is 5.1, the sampling distribution which related to normal distribution. Okay, so this is one of subtopic which is related to normal distribution as well, but here we call it central limit theorem or CLT. Okay, so by theorem 7.4, okay, let y1, y2 until yn be independent and identically distributed. Okay, this one sometimes if you read paper, they use IID. Okay, with expected yi equal to mu, expected variance yi equal to sigma square, which is less than infinity. So if you look here, you can see that it's quite similar with normal distribution, isn't it? All right. So define un equal to summation yi minus n mu, whereas I from 1 until n divided by sigma square root n. Okay, so this one, okay, you also can rewrite as y bar minus mu divided by sigma over square root n. Okay, so where your y bar is 1 over n summation of I from 1 until n. Okay, so this one clear, this is mean actually, and then here actually is a central limit theorem. Then the distribution function of un, okay, which is this one, converge to standard normal distribution function as n goes to infinity. So this is what we have here. So the limit n goes to infinity, the probability un less than u will give you negative infinity to u, and here is a normal distribution function, okay, normal density function. Here you can see that your standard normal is sigma is equal with 1, mu equal with 0. Okay, standard normal ni usually you will have mu equal to 0, sigma square is equal with 1. So when you substitute the value into the PDF function of normal distribution, you will get this one for all u. Okay. Notes here, okay, the central limit theorem implies that probability statement about un can be approximated by corresponding probabilities for the standard normal random variable if n is large. Okay, usually if you remember, when n is greater than 30, we'll ensure that this distribution of un can be closely approximately to normal distribution. So in previous subject, which is applied statistics, we always say usually when we have sample size is greater than 30, okay, the sampling, okay, can go or can approximately to normal distribution. Okay, so as a matter of convenience, okay, the conclusion of the central limit theorem is often replaced with the simplest statement that y bar is asymptotically normally distributed with mean mu and variance sigma square over n. Okay, so the central limit theorem can be applied to a random sample, whereas y1, y2 until yn from any distribution as long as the expected variance for yi is equal with mu, and the expected variance, the expected mean, okay, here, the expected mean for yi is mu and the expected variance for yi is sigma square are both finite and the sample size is large. Okay, so that's the central limit theorem concept. Okay, so look at example 7.8, page 372. Okay, achievement test score of all high school senior in a state have mean 60 and variance 64. And then you can see here, here you have mean and then you have variance. Okay, a random sample of n equal to 100 students from one large high school had a mean score of 58. So you can see that this one come from 100. So here will be your y bar or x bar lah. In this case, y bar. Okay, but here you can see this is your mu equal to 60 and here your variance is equal with 64. So is there evidence to suggest that this high school is inferior? Okay, calculate the probability that the sample mean is at most So at most is greater than or less than, okay, less than 58. Okay, yeah, I think less than, yeah, when n equal to 100. Right. So here if you look, okay, this example illustrate the use of probability in the process of testing hypothesis later. Okay, in the next chapter you will learn that. Okay, so this is the solution. Okay, using the statistical table formula as well lah. All right, so you can see that let y bar denote the mean of random sample of n equal to 100. Okay, from a population with mu 60 sigma square to 64. Okay, now we want to approximate y bar less than 58. Okay, so actually to find the probability of this one lah, y bar at most 58. We know from theorem 7.4, which is central limit theorem, isn't it? Okay, y bar minus mu over sigma over square root n has a distribution that can be approximate to a standard normal distribution. Therefore, using table 4 appendix 3, which is from your textbook, okay, but from your statistical table formula, you can find it from table 3. Yeah, table 3, page 31. Okay, page 31. So basically you have this probability y bar less than 58. So here using the central limit theorem, which is y bar minus mu over sigma over square root n. So which is sigma here is 8, square root n is 10. Then you get this. When you simplify this one, you get negative 2.5. So if you look negative, you can see that the area is at the right or the left? At the left. So now look Z 2.5, you will get 0.0062, okay, which is here 0.0062. Okay, so because this probability is so small, okay, it is unlikely that the sample from the school of interest can be regarded as a random sample from the population with mu 60 and sigma square 64. Okay, so the evidence suggests that the average score for this high school is lower than the overall average of mu equal to 60. Okay, because you can see this, the probability is very small. Okay, so it will not be average score for this is lower than the overall, because this one less than 58 kan, and then the probability is 0.0062, very small. So that means it will be lower than the overall average of mu equal to 60. All right, so that's the use of central limit theorem. Okay, and then example 7.9. Okay, page 373. The service time for customer coming through checkout counter in a retail store are independent random variable with mean 1.5 minutes and variance 1.0. Okay, so you can see that here is your mean, okay, 1.5 mean, and then the variance. Approximate the probability that 100 customers, so this is n equal to 100, can be served in less than 2 hours of total service time. Again, we will use statistical table and formula. So now you look, what is your yi? Yi is the service time for the I customer. Okay, then you will have how many customer? 100 customer. So this is the summation of 100 customer, which is less than 2 hours. Okay, because here we use minutes, so we change 2 hours to minute, which is 120 minutes. Okay, that's why here is 120 minutes. So the summation of I, okay, for 100 customer though should be less than 120 minutes. Okay, can be served like that. So you know that this is 120 minutes. How many samples you have? 100. Okay, because here yi. Okay, so how you get y bar? Okay, so this is summation of yi. Okay, when you get y bar will be summation of yi over 100. Okay, so that's why here you will have 120, and then here minus mu. 120 over 100. Okay, this one you get is 1.2. Okay, now because the sample size is large, okay, the central limit theorem tells us that y bar can be approximately to normally distributed with mean mu and variance this one. Okay, so here you can see that from previous theorem you have done this before as well. Okay, when we have y bar, the mean will be mu as well, but the sigma square, the population variance, the sample variance for y bar will be sigma square over n. Okay, because we know this is sigma square and this is mu, so we can use this information. All right, so then you have 1.5 for mu, and then for variance, okay, for the sample mean here you will have 1.0 divided by 100. Okay, so here you use the same method, okay, which is find the probability y bar minus mu over 1 over square root 100. So you can have this one. Okay, what is your y bar? Is this one. So you substitute, you simplify, you get -3. Okay, so when you get -3, you look your Z table, which is page what? Just now I said page 31. Okay, page 31, you get -3. So here you can again see it's at the left side, -3 here. So when you look -3, it will give you 0.013. Okay, this one. All right. Thus, the probability that 100 customer can be served in less than 2 hours is approximately 0.0013. Okay, very small. This small probability indicate that it is virtually impossible to serve 100 customer in only 2 hours. So it's very impossible lah. Within 2 hours we can we can serve 100 customer because the probability is very small. So that's the application of using the central limit theorem. Okay, so you can try do the exercise, okay, 7.42 until 7.61, but this one is very easy lah. Okay, it's application of central limit theorem to find the probability for using central limit theorem. But the most important thing here is theorem 7.4. Okay, you must understand the central limit theorem, which is theorem 7.4. Okay, it's come from standard normal. It's come from standard normal, where your mu is equal to 0, your variance equal to 1. Okay, so I think that's all for this video. Okay, just to introduction for the central limit theorem. But in the next video, you will have the proving of the central limit theorem. All right, class. Thank you.